In the previous session, we had learned how to use complete case analysis and available case analysis, as well as factoring the likelihood in context to missing data problems. So, now we know what to do if we have missing completely at random or missing at random. But what if we have more general missing, that is missingness which cannot be categorized into this MAR and MCAR? This is where an algorithm called the EM algorithm comes to our rescue. The EM algorithm basically consists of two steps, the E step or the expectation step and the M step or the maximization step. So, in today's session we would be discussing about EM algorithm and we would see a simple application of EM algorithm. The objective here is to get an introduction to the EM algorithm. Now, we have known about how to use or analyze data having MCAR and MAR missing data patterns. But what about finding the maximum likelihood estimate of mu and sigma under more general missing data situations? So, these are situations which do not fall under this missing completely at random or missing at random, which are generally called the monotone pattern of missing. In theory, it is easy to write out the likelihood function, because the likelihood function is a product of multivariate normal densities. But the problem is that for incomplete data, each term can involve slightly different parameters. So, the parameters for each term would be different if the data is incomplete. Now, to rescue us from this situation, there is an algorithm called the EM algorithm. The EM algorithm is an algorithm for maximum likelihood estimate in incomplete data problems. But it is an algorithm which not only applies to missing data, and that is the beauty of the algorithm. This algorithm is applied for anything where there is an incomplete data problem. For example, we all know by now that missing EM algorithms are applied for missing data likelihood, and we would see how it is applied. But the same principle can be applied for random effects model, where the random effects are treated as missing. The same problem can be applied in context to a latent variable modeling. The same algorithm, or rather the same algorithm, can be applied in context to censored survival data. The same algorithm can be applied in structural equation modeling. So, EM is a very generic algorithm which can be applied to rather any incomplete data problem. So, what is the idea? The idea is to write the complete data likelihood and then estimate the missing parameters. Then again use the missing parameters and re-estimate, write the complete data likelihood and re-estimate the missing values. And this goes on. So, basically EM is an iterative method and the iteration goes on until convergence. The EM algorithm consists of two letters, the E and the M, and this stands for the E step and the M step. The E step is the expectation step and the M step is the maximization step. So, what we do in the M step? We perform a maximum likelihood as if we had the complete data. So, assuming we have the complete data, whatever data we have, we perform maximum likelihood. In the E step, what do? We find the conditional expectations of the missing data given the observed data and current parameter estimates. So, we get the parameter estimates from the M step and then use that to find what's the conditional expectation of the missing data given the observed data and the estimated values of the parameters. Now, we really don't go by the conditional distribution of the missing data per se, but we model the functions of missing data. Now, let us take an example to illustrate what we are trying to do. Consider the univariate normal case where we have yi follows IID normal mu sigma square and I runs from 1 to n, but suppose only m of them are observed. So, I is equal to 1 to m and m is less than n. So, the complete data log likelihood is ln L, so mu sigma square, and that is 1 by 2 sigma square, I runs from 1 to capital N, yi square minus twice mu yi plus mu square. So, we have expanded the yi minus mu whole square term minus n by 2 log 2n sigma 2 pi sigma square, sorry. Now, note that the log likelihood is linear in the sufficient statistics. So, what are the sufficient statistics here? That is summation of yi I runs from 1 to n and summation of yi square I runs from 1 to n. Now, what is the EM algorithm? Now, let us begin with the estimates mu naught and sigma naught square. So, given y observed in the E step, in the E step we assume that y observed is given, we know y observed, and suppose we are using computing the E step at the tth iteration. So, then the value would be mu t and sigma square t. So, t runs from 0. So, we know what is the value at mu 0 and sigma square hat 0, and t goes on and on till it converges, that is mu t hat equal to mu t plus 1 hat and sigma square t hat is equal to sigma square t plus 1 hat. Now, what do? We calculate the expectation of summation yi given y observed mu hat t sigma square hat t, and that comes out to be summation yi I runs from 1 to m plus n minus m mu hat t. Similarly, the expectation of summation yi square, that is the sufficient statistics, given y observed mu hat t sigma hat square t is summation I runs from 1 to n yi square plus n minus m mu hat t square plus sigma hat square t. Now, what is the m step? M step assumes that summation yi I runs from 1 to n and summation yi square I runs from 1 to n are given. Then the maximum likelihood of mu and sigma square are given by mu hat 1 by n summation yi and sigma hat square 1 by n summation yi square minus mu hat square. So, then at the next iteration, so we have started at t, so the next iteration would be at t plus 1. So, to get the estimates at step t plus 1, we use the same expressions with the current E step, that is mu hat t plus 1 now becomes summation I equal to 1 to m yi plus n minus m mu hat t by n and sigma square t plus 1 summation I equal to 1 to n yi square plus n minus m mu hat square t plus sigma hat square t minus by n minus mu hat t plus 1 square, and we iterate this until convergence. Now, this is a simple example and we can calculate a closed form solution. So, at convergence what would happen is mu hat t would be equal to mu hat t plus 1, that is the, and sigma hat square t is equal to sigma hat square t plus 1, and the mu hat estimate would come out to be 1 by n summation I equal to 1 to n yi, and sigma hat square is 1 by m I equal to 1 to m yi square minus mu hat square. So, this is the usual maximum likelihood estimate of mu and sigma square from y observed. Now, the advantage of the EM algorithm is that it can be used for much more complex problems. So, here as an illustration we have shown a simple example, but this can be used for a much more complex problem. Now, the advantages of EM algorithm is that it can be shown that log likelihood increases at each iteration under convergence. The computation is tedious, but it is straightforward, and it does not require the second derivative calculation. So, generally for maximum likelihood it requires a second derivative computation, but here it is not that. There are certain disadvantages of EM also, and the primary disadvantage is that it may converge to a local maxima. Also, the convergence rate can be slow. While now this is in contrast to Newton-Raphson's method, because there the convergence is quadratic. Now, we again illustrate the EM algorithm in context to a multivariate normal. So, initially we had shown for univariate normal, but this time for a multivariate normal how the EM algorithm works. So, for a multivariate normal with missing data, for complete data we assume that yi follows multivariate normal. So, it is a p dimensional multivariate normal with mean mu and variance covariance matrix sigma, and I is 1 to capital N. So, the sufficient statistics is summation over I equal to 1 to n yi j, j equal to 1 to p, and I equal to 1 to n yi j yi k, j k equal to 1 to p, where j less than equal to p. And the maximum likelihood estimates is mu hat ml, which is nothing but the sample mean, is 1 by n summation yi 1 up to yi p, normal in vector notations. I mean it's a column vector, and sigma hat ml is the sample variance covariance matrix. So, yi minus y bar, yi minus y bar prime or transpose, and then I can write it as 1 by n summation yi transpose minus y bar transpose. Now, we can divide the incomplete data, or we write the data into yi as yi observed and yi miss. And so, what is the E step? The E step here is expectation of summation yi j given y observed mu hat t and sigma hat t is 1 to n yi j t, while expectation of summation yi j yi k given y observed mu hat t sigma hat t is summation yi j t yi k t plus c j k I t. Now, here we have introduced this c j k I t, but let us see what these terms are. So, y I j t is y I j if observed, and y I j t is expectation of y I j given y I observed mu hat t sigma hat t if it is not observed. So, that is the conditional mean or the conditional expectation of y I j. And c j k I t, what is this? This is 0 if y I j or y I k is observed, but this is not 0 if covariance, if both y I j k y I k are missing, and then it takes the value covariance of y I j y I k conditional on or given y I observed mu hat t and sigma hat t. So, in the M step what do we have? We have mu hat t plus 1. So, which is 1 by n summation of the tth the values we obtain from the tth iteration. Similarly, we can define sigma j k t plus 1 hat, which is like whatever we observe in the tth iteration we put in the values. So, it becomes summation y I j y I k given y observed mu hat t and sigma hat t minus mu j t plus 1 mu k t plus 1, and then what we do? We use, so this is simplified to 1 by n summation 1 to n y I j t minus mu hat t plus 1 y I k t minus mu hat t plus 1 plus c j k I t, and then we iterate this until convergence. So, later on again we would be having a R session on how to implement this in R, or rather the EM algorithm in context to a multivariate normal, and how do we implement that in R. So, the question that comes is, what is the possible starting values of mu naught and sigma naught hat. Now, it comes that the complete case or the all available case estimates starts as a very good starting point in this sort of problems as a initial value, and then we can iterate using the EM algorithm to get the value or the estimate of the parameters. So, in this session we were introduced to the EM algorithm. The EM algorithm is a exceptionally useful algorithm for incomplete data cases, and we have used the application of EM algorithm for missing data in context to univariate normal and multivariate normal. Now, the advantage of EM algorithm is that it has wide applicability, and it is not restricted only to missing data problems, but to other problems like random effects model or censored survival data and this sort of models. In the next session we would be seeing what are the properties of the EM algorithm. So, what are the properties for which EM algorithm has become so popular in statistics literature.